Welcome all of you. Yeah, since last couple of classes, we have been discussing about scalar coupling. In the last class, I introduced you about the coupling between two spins and three spins, and I also introduced the concept of spin system and also what is strongly coupled and what is the weakly coupled spin system. And we worked out for a multiplicity pattern for two coupled spin systems, and I wanted to tell you how we got the intensity pattern, how we got the splitting pattern. We start with a simple one spin system. For example, in CHCl3, we are going to get a single peak that we observed. And then I took the example of two weakly coupled spin systems, and I showed that we can get two peaks, each for A and each for X, and they are of equal intensity. I also showed there is a center of the doublet corresponding to respective chemical shifts. Center of the doublet of A correspond to chemical shift of A, center of doublet of X corresponding to chemical shift of X. This is what I said. And also I showed what happens if there is a splitting of energy levels, how the intensity comes down by a factor of 2. So with this, what we will do is, we will continue further today, and let us see how far we can go together with further introduction or further discussion about scalar coupling. It's a very, very important parameter in NMR. So you must concentrate and try to listen, try to understand as much as possible. Remember, I said in the previous class, interaction among spins in NMR are always mutual. Okay, I said if proton A is coupled to X, proton X is also coupled to A. It is a mutual interaction. And I showed in the two spin case, when two coupled spin, if peak of proton A is split into doublet, because of its coupling with proton X, I also said doublet with identical splitting is also seen for proton X, because proton X also sees the two spin states of proton A. So this is one of the very important point you should remember. Interactions in NMR among the spins are always mutual. I showed in the last class about this, the coupling pattern between two non-equivalent spins. I took the example of a hypothetical molecule like this. This I call proton A, this I call proton X. Now, when I'm looking at this one, for example, I am looking at the proton X. The proton X sees proton A in two possible spin states, that is in two orientations of A, alpha and beta, and splits into a doublet. Identically, now X, A sees X in two possible orientations. The center of this doublet corresponds to chemical shift of X. The center of this doublet corresponds to chemical shift of A, and this separation corresponds to coupling constant between A and X. It's a JAX. Okay, if you measure the simple frequency separation between these two peaks, what you are going to measure is the coupling between A and X. Okay, this now another interesting thing you should understand. I said when I was introducing to you the salient points of coupling, I said if one proton is coupled to another proton and there is a coupling which is non-zero, I showed one peak splits into two. 2 will split into 4. 4 will split into 8. Remember, I showed in one of the slides. What was happened to the intensity? The total intensity of the uncoupled spin and total intensity of the multiplicity, that is area of this, all the peaks put together, will not be different. So what happens? When one spin split into a doublet, the intensity comes by half. Now, it is half intensity. Although it appears to be equal together, it is 1:1 ratio, but compared to the one without coupling, it has reduced by 50%. Same way, intensity of this A peaks also are reduced by half. So that's why we are going to get 2 peaks for this and 2 peaks for this. Now, two coupled non-equivalent spins, JAX equal to 0. I said each proton gives a doublet with identical separation. Intensity is equally divided between two peaks. Equally divided between two peaks. This asymmetric intensity pattern is not seen in NMR. Now, please remember this asymmetric intensity pattern because interactions are always mutual. And the separation I said gives JAX. I'm repeating this point just to make sure you understand this. The separation of each doublet gives you JAX. Center of each of these doublet gives you corresponding chemical shields. This is the salient point which I said when two coupled spin systems are there with J coupling non-zero. We have a realistic situation where two spins are coupled. I show you the spectrum now. Look at this molecule. There is some substitution here. These are three methoxy groups and these are the two protons which are separated by three covalent bonds. Now, if I take the proton NMR spectrum of it, it looks like this. Look at it. Now, what is happening is A has two orientations, X has two orientations, which so far we were discussing. As a consequence, you see, A is a doublet, X is a doublet. A is coupled to X and becomes a doublet. X is coupled to A and becomes a doublet. You understand? This is a two spectrum of two coupled spin system. And I was telling you about strong and weak coupling. I introduced the term strong and weak coupling. I said when the chemical shift separation is larger than the separation, this coupling constant, then it is weakly coupled. Look at this chemical shift here. It is about 6.7 ppm here. It is about 7.5 approximately. So 7.5 and 6.7, 0.8 ppm. Remember, 0.8 ppm is a huge value. At a 500 megahertz, 0.8 into 500 is 400 hertz. Coupling constant may be of the order of 10 hertz. 10 over 400. It is nearly, this coupling, this chemical shift separation is nearly 40 times larger. So, this is a weakly coupled spin system. That's why I call it as A and X. We'll talk more about Popple spin nomenclature, weak and strongly coupled in subsequent classes. There, detailed discussion will be there. I'll discuss with you all these things. But one interesting thing you must understand, in a weakly coupled system like this, AX or AMX, whatever you say, take the intensity pattern should be always equal. They must be of equal intensity. Here, look, there is some sort of an intensity anomaly here. Intensities are not equal. Strictly speaking, even at a particular spectrometer where it is recorded, although chemical shifts are far away separated, the intensities are not equal. So, there is a minute strong coupling character present in the system. But nevertheless, for the purpose of analysis, this chemical shift of A and X can be obtained. This separation gives me J coupling. Okay. So, this is the realistic situation. This separation gives J, this separation. And now we will go to more complex multiplicity patterns. Remember one important point, coupling of a proton with chemically inequivalent protons. Chemically inequivalent. In which case, we can obtain the splitting pattern by what is called a family tree approach. What is a family tree approach? Husband and wife gives, now they have 3 children, each of them get married, I have their family, each of them may get 3 or 4 children. 1 will become 2, 2 will become 4, 4 will become 8. Like a chain reaction, it keeps going on. This approach is called a family tree approach. So when one proton is coupled to n chemically equivalent protons, we can go by what is called a family tree approach to understand the splitting pattern. Okay, let me explain to you. Let us consider the example of one proton coupled to 2 other non-equivalent protons. Just now we discussed 2 protons coupling. One is coupled to other one, single proton, that's fine. That is a 2-spin case. Now I am considering 3-spin example. One proton is coupled to 2 other non-equivalent protons. Let us see what it is. I am taking an example of a hypothetical molecule like this. This is some other substitution X, so that all these 3 protons are chemically inequivalent. I have deliberately taken. Okay, it is just a hypothetical molecule, not a realistic situation. I am trying to tell you realistic molecule. I am looking at the proton X. which is highlighted with a light pink color here. Okay, look at this proton X. How? What is the multiplicity of this proton X when it's coupled to A and when it is coupled to M? That's what we'll understand now. Now, assuming there is no coupling with proton A and there is no coupling with proton M, X will be a singlet. Correct? Like we understood the single spin situation, CHCl3 we saw, right? When only one spin is there, no other coupling, we get a single peak. It is an isolated spin system. When the assuming couplings are 0 with X, we get a single peak. X, fantastic. And call this intensity as 1, 100%. Full intensity is there. Now, what I will do is, I'll bring in the coupling of this with proton A. What are the possible orientations of proton A? Alpha and beta spin states. Now the proton X sees proton A in two possible states, two possible orientations. See, the magnetic moment of proton A is alpha and beta in the magnetic field. So this is two different energy states. So as a consequence, when it interacts, we understood it has two different energy states, splits into doublet. See, we understood the mechanism of coupling, you know. So as a consequence, there is polarization transfer takes place between A and X through covalent bond, and this peak splits into a doublet. Now, what is the intensity of this doublet? This is 0.5 and 0.5. One has been divided into two. Like in the family tree approach, I said family property from 1 divided to 2 children, 50-50. So the intensity is divided into half. As I said in the earlier case, this separation tells you the interaction strength between this proton and this proton. That is JA. Clear? We understood that. Now, we will extend the logic further. Now, I bring coupling of proton X with also proton M. Okay? Now, when I bring this, what is going to happen? This will further, each of this line splits into doublet because M is coupling to X again. So, one was splitting into two. Now, again, because of course I taken some coupling strength here, I don't know what it is. This M is coupled to X and split each of this line into a doublet. Please remember, each of this line is split into a doublet. And what happened to intensity? It is 0.5, 0.5, now came down to 0.25, 0.25. Again, it is divided to half. The property of one family was full, 100% property was there. Now, it was divided between two children. It became 0.5, 0.5. And each of these children had further two children, and it was further divided and 0.25, 0.25. Like a family tree approach, it was a division. Intensity got divided like this, 0.25, and again this is 0.25, 0.25. So this was the interaction strength between A and X. This is the interaction strength between M and X. Okay, so what does it mean? One spin, X, when coupled to two other spins, you will get doublet of a doublet. A will split X into 2, M will split further into 2. You are going to get 4 peaks of equal intensity. Remember, it is the intensity might have come down by 1/4 compared to uncoupled proton, but the intensity pattern, if you see, all are equal. It is 1:1:1:1 ratio. You understand? This is the coupling pattern of one proton when it's coupled to other two protons. And this pattern depends upon what is called the coupling strength. That's fine. Whether this is larger or this is larger depends upon that. The pattern can be worked out, which is the coupling and everything. I'm just giving you an example of splitting pattern here. We'll go more when to extract the coupling in the from the spectrum. At that time, we'll try to understand all those things. But one point you remember in the salient points when I discuss about the interaction strength of about the scalar couplings, one of the important point I said was each nuclear spin can experience coupling with all other chemical NMR active spins which are chemically inequivalent simultaneously. So I am giving an example, first X coupled to A and then TM. No, it need not have to go in this order. It can be any order. Only thing is simultaneously this is interacting with this is also interacting with this. At the same time, this proton experiences coupling with these two. Tomorrow don't come and tell me, hey, first it has to interact with this and then this. No, there is no sequential operation like that. One proton, simply understand, simultaneously experiences coupling with all the other NMR active spin so long as there is an interaction between them. Okay. Now I was concentrating on this proton X. Forget it. Now I look at the proton A. When I see proton A, what is the type of splitting I am going to get? Remember, this proton A, again, similar to X, experiences coupling with this. What happens? It will become a doublet. Further, this proton A also experiences coupling with this proton M. So, simultaneously, this also experiences two couplings. So, proton A, if I look at it, again start with proton A here, split into two because of AX coupling, and then split further into two because of AM coupling. So, what happens? Again, you get four-line pattern of equal intensity. Remember, I said four-line pattern, but I didn't say identical pattern. The pattern can be different. Please understand, pattern can be different because here this coupling and this coupling there are two different couplings, and this coupling may be larger and this coupling may be relatively less. But when I look at this is one coupling and this coupling may be smaller. This is, I'll tell you when you go further about cis and geminal coupling, vicinal coupling, etc. So coupling strengths will be different. This proton experiences two different couplings. Similarly, this proton experiences, this coupling may be same, but this coupling is different. So you get four lines of equal intensity, but the pattern may not be same. I have written here as if four well separated lines. It so happens this line may come closer, or these two lines may become closer because this coupling is smaller. It can happen. But remember, pattern is identical. Okay, I mean splitting pattern, but the separations can be different. Okay. Now what happens if I observe M? Will I get the same pattern? No. Remember, this M experiences coupling with this X. It's a three-bond coupling. And in addition to that, this experiences coupling with A. It is a two-bond coupling. So this coupling is quite large. Okay. And then this coupling is quite small. So it is a large doublet, and each of this doublet split into smaller doublets. So this pattern, again you get four lines of equal intensity, but pattern is different from this and this different from this. Very interesting thing, is it not? It is a three coupled spin system. If I take one proton coupled to two other non-equivalent protons, it so happens each proton gives rise to four peaks of identical intensity, 1:1:1:1:1 ratio. But I'm sorry, but the separations between the peaks may not be identical because the coupling strengths are different. In this example, I'll give you further. Please understand. This proton coupling is three bond trans. This one three bond trans and three bond cis. This proton experiences three bond cis and two bond geminal. This experiences three bond trans and two bond geminal. So all the couplings may not be same. So the fact you get four lines of equal intensity with a different separations due to different coupling strength. Remember, when we understood the three spin system AMX, I observed the transition. I allowed what are the allowed transitions. and we observed that, through the energy level diagram, we observed 12 peaks of equal intensity, 4 for A, 4 for M, and 4 for X. Remember? Exactly, this is the realistic situation now. You get 4 for X, 4 for A, and 4 for M. So, you are going to get 12 line pattern. This is an example when one proton is coupled to two other protons of different strengths, chemically inequivalent protons. Now, extend the logic. Now I will take 4 coupled spin system. Simple logic. How many peaks I must expect? Start extending the logic. When 2 protons were there, when 1 proton was there, you get 1 line. When 2 protons are there, you got 4 lines. When 3 protons were there, you got 8 lines. I'm sorry. When 2 protons were each one got 4 lines. So 1 proton is single line, 2 protons 2 lines, and when 3 protons are coupled, each one you got 4 lines. Now we will see what happens when 3 protons are coupled. That is, 4 protons are coupled. 1 is coupled to chemically non-equivalent 3 other protons. So now this is a hypothetical molecule. Again, consider proton X. You understood coupling with A. This in the previous example. We understood this also. Coupling with X will couple to A, doublet, and X will couple to M, doublet of doublet. Now what is the new thing? We have brought another proton, third proton, P. What will happen? Each of them will further split into half. So what is the intensity now? This was intensity 1, 0.5, 0.5, 0.25, 0.25, 0.25, 0.25. Again further divided into 2, 0.125, 0.125, 0.125, 125. All 8 lines are of equal intensity with 0.125 intensity. Add up all these things. 0.125, 0.125 becomes 0.25, 0.25, 0.25, 0.25. So total intensity is 1. What is this intensity total? 1. So this is what, when I was explaining to you the salient features of the coupling pattern, I said the total area of the peak of uncoupled proton or uncoupled spin is same as the total area when you get the area of the multiplicity pattern. When they are split, take the total area. This and this remain same. We understood now very nicely. We got this gas is a JX coupling. This I brought in the another coupling with JMX. This separation gives you JPX coupling. So what? How many peaks you got? When one proton is coupled to 3 other protons, you got 8 peaks. Now, what is the pattern you are going to get for other protons? I observed X here. What happens if I observe A? A again is coupled to 3 protons. Similarly, work out the family tree diagram for proton A. A is coupled to X, A is coupled to M, and A is coupled to P. So, you will get 8 lines of equal intensity for A. Similarly, for M, M is coupled to A, M is coupled to X, and M is coupled to P. You get again 8 lines of equal intensity for M. What about P? Exactly same, 8 lines of equal intensity. But like I said in the previous example, the separations are not same. If when I took this one, this had a cis coupling and a trans coupling and another long range coupling. When I took this, it has a cis coupling and a geminal coupling. It doesn't have a trans coupling. Whereas when I took this one, it has a trans and geminal but doesn't have a cis coupling. So the coupling strengths are different because it experiences different types of coupling, but the pattern of 8 line remains same. Although the separations are different. You understand? So this is the logic now. Let us go by the logic. What is the simple logic now? When I have a n non-equivalent protons are coupled, how many peaks we expect? Go by the logic now. When one proton was coupled, you got one line. Isolated proton was there, you got a single peak. Now there are 2 protons were coupled. I was observing 1 proton. At the site of that 1 proton, At the chemical sheet of that proton, how many lines we get? 2. When one proton is coupled to 2 other protons, how many we got? 4 lines. When one proton is coupled to 3 other protons, how many lines we got? 8. So what is the logic? Logic is very, very simple. The number of transitions when one proton is coupled to n chemically equivalent protons is simply given by 2 to the power of n. I'll come to that later. Okay, there is some other thing which I want to tell you. When one proton is coupled to another proton, gives a doublet of equal intensity. This is what I explained. When one proton is coupled to 2 different protons, gives 4 lines of equal intensity. When one is coupled to 3 different protons, gives 8 lines of equal intensity. This is summary of what I was telling you. I have written explicitly here. Now coming to the logic. When one proton A is coupled to M and X, A gave 4 lines, M gave 4 lines, X gave 4 lines. So totally we got 12 lines. Fantastic. Now we come to a general formula. For n different protons coupled among themselves. Now, what is the logic? The number of lines at the site of one observed proton is given by 2 to the power of n minus 1. Okay. What is this formula I am writing? You understand? At the site of one of the observed proton, let us consider, we look at this thing now. I have 3 protons, 1, 2 and 3. I am looking at this proton. At the site of this proton, I'll take 3 protons coupled. How many peaks I expect? It is totally there are 4 coupled spin system. N minus 1 is 3. So leave apart this proton which you are looking at. How many are there to be which are coupled to it? 3. So what is 2 cube? 2 to the power of n minus 1 is 2 to the power of 4 minus 1. That is 2 cube here. So what is 2 cube? Which is equal to 8. Okay. So that is what we observed. When 4 coupled spins are there, when you observe one proton, it is coupled to 3 other protons. As a consequence, it gave rise to 8 lines at this position. Now I am going to take, let us say, another proton. This, and this. Now I am looking at this proton. What happened to this proton? Again, it is coupled to remaining 1, 2, and 3. So 2 to the power of 4 minus 1. There are 4 protons. You have to minus the 1 because this is what you are observing. You have to consider only the remaining spins. These are the remaining 3 spins. So 4 minus 1, 2 cube. So this also gives 8 peaks. I'm sorry, 8 peaks like this. What about this one? Now I'm going to observe, okay, this peak, this one. What will happen? This is observing there are 3 remaining protons here. Again, 2 to the power of 4 minus 1. This also gives you 8 lengths. Look at this one. This proton. This is observing it is coupled to remaining 3. Thus, this also should give you 8 peaks. So what is the formula I am telling you now? Remember, simple, when n protons are coupled, at the site of any of the protons, if you consider, okay, at the site of any of these proton, the number of allowed transitions are given by 2 to the power of n minus 1. Understand the logic? When 4 protons are coupled, 2 to the power of 4 minus 1, 8 peaks you get, 2 cube, at each proton. Now how many protons are there? 4 protons. So totally how many lines you get in the entire spectrum? This is at the site of one proton, one spin. Now 4 are coupled. So totally you will get n star 2 to the power of n minus 1. Now plug in the parameters here. 4 start with a 2 spin. When n is equal to 2, 2 minus 1 is 1. So it is 2 spin and n is 2, 2 into 2, 4 lines. Exactly. That's what we observed when 2 protons are coupled. You will go even one level lower. What happened when n is equal to only 1 isolated proton? Like CH-Cl3 we took example. When n is equal to 0, I'm sorry, n is equal to 1. 1 minus 1 is 0. 2 to the power of 0 is 1 into 1. So in an isolated single proton spin system like CaCl3, without any coupling to other carbon 13, etc., you get in a single peak. Now I took the example of two spins. When n is equal to 2, 2 minus 1 into 2. See, n is equal to 2. 2 minus 1 is 1, 2 to the power of 1, 2 into 2. So when two protons are coupled, totally you get 4 lines. 2 for A, 2 for X. Now take the example of 3 spins. When n is equal to 3, 3 minus 1 is 2. What is 2 square? 4. 4 into 3, 12. So when 3 protons are coupled, you get 12 lines, 4 for A, 4 for M, 4 for X. That's what we observed. Now, this is the last example I took. N is equal to 4. 4 spins are coupled, A, M, P and X I took. Now, 4 minus 1 is 3. What is 2 cube? 8. So, at each proton's chemical shift site, you get 8 lines. There are 4 such protons coupled. So, 4 into 8, 32. So, when 4 protons are coupled, the entire spectrum, there will be 32 lines. When 3 protons are coupled, the entire spectrum, there will be 12 lines. Like this formula tells you how many peaks you get when n different chemically equivalent protons are coupled. This is a simple logic. Now, this is taken from one of the websites of Reich from University of Wisconsin. I tried to get the permission from him by writing email. Somehow the email bounced back. I have taken the example, so I would like to acknowledge him here. So this is what I want to tell you. The spectral pattern when one proton is coupled to n other protons. For example, one proton is coupled to 3 protons, you get 8 lanes. 1, 1, 1, 1, 1 of equal intensity. But here there are 2 overlapped. So there are 8 lanes here. 1, 1, 1. This is 1 plus 1, 2 are overlapped. So 8 lanes. When one proton is coupled to 4 other protons, very 2 to the power, and I understand when 1 is coupled to 4, how many you should expect? 16. Why? You see 1, 2, this is 3, 4, 5, 8, 11, 12, 13, 15, 16. Some are overlapped. They have 3 are overlapped here, 2 are overlapped here, 2 are overlapped here. So when 1 is coupled to 5, more interesting. How many you should get? 32 peaks. One proton. These are all not that all the time you get in the realistic situation. Just to show you, when one proton is coupled to n other protons, restricting simply you go by the family tree approach, and this is how you can understand the multiplicity pattern. Remember, in my formula, now you are going to get 32 peaks when one is coupled to 5 other protons. That means the total number of coupled spins are 6. So then how many you should get in the entire spectrum? N, I wrote the equation sigma of n star 2 to the power of n minus 1. That is 32 into 6. Is 192 lines we get in the spectrum. Very complex spectrum. Like that, you can work out how many lines you get for each of these things. So, in this, take an example here. Let me work out and tell you. All of you should be in a position to work out now. One single proton is coupled to 4 other protons. How many peaks you got here? 16. So, but total number of spins are 5. So, we are observing 1, remaining 4 are coupled. So, there are totally 5. 5 into 16. 80 peaks are there in this. Very, very difficult, you know. So, 80, so 5 into 16, right? 25, 60, 16 into 5. 80 peaks will be there in this entire spectrum. So, this is what the important thing I wanted to tell you. Multiplicity pattern, when you want to understand how to go ahead and analyze, is a very, very important thing. Simple. In all these things, I have taken the example of chemically inequivalent spins. Please observe what I was taking example. In each of them, I was taking one proton coupled to another single proton, like H only are coupled. But in the realistic molecule, it may not be like that. There may be a CH proton here. Next may not be CH, it may be CH2. Next may be CH3. They are all equivalent spins. So far, I have not discussed about coupling to equivalent spins. I am discussing only coupling of individual spins which are chemically inequivalent, and we arrived at the number of peaks that we can expect at each chemical site of the proton, and what is the total spectrum you are going to get in the entire spectrum. You understand? This is what I was discussing. I have told you everything today. So with this, we will stop here today. We'll come back and continue further about more on about splitting pattern and analysis of the spectrum tomorrow.